Good afternoon, everybody. It's a pleasure to welcome you to the fourth edition of our graduate seminar series. I'm Jean-Philippe Leal Silva. I'm an assistant professor at the Department of Process Engineering here at the School of Chemical Engineering. This event was created to promote research in other institutions and bring your students closer to foreign researchers. So you can see this is a networking strategy to promote the internationalization of the graduate program in chemical engineering. And when we talk about networking, this includes both our very distinguished speaker, Benjamin Bursik, and networking among the students themselves. It's a desire among the professors of the School of Chemical Engineering to create opportunities for engagement between the students of different research groups and laboratories. So after the lecture of a distinguished speaker, we will have a coffee break served over there in the hall. So you can get to know each other better and exchange ideas with your graduate school colleagues. Remember, the event was created for you. And I have a very important announcement. The next elections for a student representative will happen very soon. Flávia Ferreira, please stand up. Okay, Flávia is here. Flávia is the current student representative. She's here, and I encourage you to talk to her to know a bit more about the role of the student representative in the Graduate Studies Commission and how you can help to improve the graduate program. We need candidates. I think that's enough for a start. Let's go to the most important part of the event. Our distinguished speaker today is Benjamin Bursik. Benjamin is a PhD candidate in the field of molecular thermodynamics at the Institute of Thermodynamics and Thermal Process Engineering, ITT, at the University of Stuttgart. His research focuses on developing theoretical models to study fluids in porous media. Starting from the interactions of individual molecules, he investigates dynamic processes that are relevant in a variety of applications, such as fuel cells, underground water systems, or biological tissue. Currently, Benjamin is conducting a 3-month research stay with Professor Luis Franco, where he applies molecular models to a adsorption process for the capture of CO2 from exhaust gases. His master thesis at ITT involved deriving a model for surfactants, which are commonly used in soaps or as emulsifiers. As an undergraduate, he spent 1 year at the University of California, Berkeley, broadening his academic experience in thermodynamics and fluid dynamics. The title of his talk is Interfaces, Transport, and Engineering, a molecular perspective on solid fluid systems. Benjamin, on behalf of the director of the School of Chemical Engineering, Professor Dirceu Noriller, and the graduate program chair, Professor Melissa Vieira, I would like to thank you for being here today. Welcome, and the floor is yours.
Hello everybody. Thank you very much for the nice introduction, and thank you, Professor Luis, for the chance for me to be here. And thanks guys for coming to my presentation. As Jean said, it's about interfaces, transport, and engineering, and I would like to give you a molecular perspective on solid fluid systems. I guess I can more or less skip the short biography part because I was already introduced very nicely. Yes, as he said, I am at the University of Stuttgart right now. I'm a PhD student there. And right now, since January until next week, I will be here as a visiting researcher with Professor Luis and his group. Before that, I did my master and my bachelor's both at the University of Stuttgart. I did internships at the BASF, a big chemical company in Germany, and I did a year abroad at Berkeley in California. In my presentation today, I would like to start off with giving you a short introduction into the field of molecular thermodynamics, just to get an idea how we look at things in this field. Then in the second part, I want to talk about my research on solid fluid systems. And then the third part, I will introduce the work that I have done here. This will be about applications of molecular theories to an actual engineering process. And finally, I will be talking about the life and the PhD in Stuttgart in Germany, what you could expect if you might like to go there. Okay, this will be a very, very short introduction. Make sure this is a huge field and it could take months and years to study this, but I want to give you the perspective of how we approach problems in this area of research. So starting from a real-world application or a real-world phenomenon, something you see on your everyday life, right? For example, in a glass of water, there you could put a paper clip on top and it would not immediately sink down to the ground, but it would stay at the top. Or insects that could walk on the water in a lake, for example. The reason for that is, of course, the surface tension, as I guess you know. But if we look at a molecular scale, so if we zoom down quite closely to the interface is not just a jump from liquid to vapor, right? It's actually, when you look at the density, it's a transition from a liquid phase, continuously the density going down to the density of a vapor phase. And if you look at the molecules in this case, so you have molecules in the liquid phase, which are quite close to each other, and in the vapor phase, where the molecules are further apart. And in between, there's a transition region between these two cases. So the overall goal of molecular thermodynamics is now to look at the interactions between the molecules, to then determine how this density profile looks like, and from that, to calculate the surface tension. Basically, to make predictions about surface tensions at different temperatures, pressures, different substances, mixtures, all of that. In my work, as Jean said, I'm talking about, or I'm working with solid-fluid interfaces. So I'm going to briefly talk about this. Specifically, I'm going to talk about adsorption a lot. Adsorption is the process where molecules attach to a solid. And this is not the same, and it's important, it's different from absorption, where molecules go into a liquid phase. So I will not talk about the right part, only about the left part today. Again, if we look at the density profile on a really, really small scale, this can look a bit interesting with maxima and minima in the density. And this is caused by a molecular layering of molecules at the solid interface. And why is this? This is caused by solid-fluid interactions, molecular or atomic interactions that we want to look at. In the field of molecular thermodynamics, we often think of it as an external potential, which the solid acts on the fluid. So you have this minimum here, and minimum energy is the place where the molecules like to stay the most likely. So this maximum here in the density corresponds to this minimum in the external potential. And again, the goal is to use molecular theories to determine this density profile, and then to, for example, integrate this density profile to know how many molecules adsorb to a solid. So for example, how many moles of a gas adsorb to a solid per kilogram of this solid. Because this is an input in many applications in industry, for example, as I will show later. Okay. I will introduce two important approaches because these I will talk about a lot later in my when I present my research. So this will be molecular dynamics simulations and classical density functional theory. Molecular dynamic simulations are a method where we start by looking at individual particles in the fluid or in the solid phase, and we track the positions and velocities of each of these atoms. Then we use Newton's equation, we integrate these, and we do that for many, many, many time steps. So we know how the atoms move in our system. Remember, this is really, really a small scale. We're looking at a few hundreds to a few thousands of molecules here. And then we can determine quantities like the density profile, kinetic energy, potential energy, and many more by taking ensemble averages, meaning we average over all the different time steps that we integrated before. On the other hand, we have classical density functional theory, where we directly use average quantities, such as the density profile, and we use methods from statistical mechanics to, for example, minimize the energy in a system and determine how the density profile would look like in an equilibrium case. The advantage of the left method is that it's much more detailed. It gives you a lot of more details, and it's quite predictive. You don't need so much input, but it is quite expensive in a computational sense. It takes a long time, basically. And the other hand, classical density functional theory is much more efficient, but you need a little more information, a little more input, and you get a bit less detail out of it. Okay, this is all I want to talk about for the introduction to molecular thermodynamics. And I will now go on to my research that I did before coming here. So my research back in Germany on solid fluid interfaces. And the solid fluid systems we often call porous media. So basically you have a solid with a lot of tiny holes, and you have a lot of interface between solid and fluid, and this brings many interesting properties. So why do we care about these kind of systems? There's a lot of applications that are interesting. For example, underground water systems, or in technological applications, for example, in fuel cells, you have these diffusional porous gas diffusion layers where the gas is transported to the electrodes. You could also view the human body as something like a porous system. Example, the blood in your arteries. It is a liquid that flows through something that is more or less a solid, or could be viewed as one. So there's a lot of applications, but at the same time, it's quite difficult to model such systems because you have to look on a macroscopic scale. This is the scale of our everyday life, like the big scale, to get how the system looks like. But you also need to look at the pore scale or even the molecular scale to understand how interfaces can affect the overall system behavior. So in my research, the overall goal is to connect molecular modeling with continuum scale equations, something like Navier-Stokes balance equations, for example. Yes, I will shortly give you an overview of my research projects that I will present today. First of all, I worked with density functional theory, so the method on the right on the 2 slides before. And there I looked at interfaces and equilibrium with 2 applications that I want to show you and the comparison of our results to experimental data. Then in my PhD, I looked at entropy scaling, an approach for determining transport coefficients, something like viscosity, diffusion coefficient, thermal conductivity. But due to the time limit today, I will skip this part and just use what we developed there. Finally, I will present the main part of my PhD that is about hydrodynamic DFT. It's a version of DFT for dynamic systems, obviously, as the name says. It's a combination of balance equations with this microscopic or molecular DFT model. And with this approach, we can then look at dynamic processes, for example, droplets that move over a solid surface, or, and look how these droplets deform, and many other interesting applications. Here, because we're on a really, really small scale, it's difficult to do experiments, so we compare to molecular dynamic simulations. These are typically used as some kind of reference for our model. Because they provide really exact, really accurate results. Okay, let's start off with classical DFT. As I said before, we work here with a density profile and we minimize the energy of the system by doing this. I'm not sure if you've heard of the term ensemble. This is basically a system where you have a clearly defined variables that are constant. So in our case, this is the chemical potential mu, the volume V, temperature T, they are constant, and all the other variables are a result of basically the calculations. This grand canonical functional, omega, functional is a term to say that it depends on the density profile instead of just one value of the density, consists of 2 relevant terms, so the Helmholtz energy here and an external potential here. We then use the basic message of DFT is basically that in equilibrium, this functional has its minimum. So we can derive, or we can take the derivative, set it to 0, and determine an equation from which we can then calculate the density profile in equilibrium. We then want to look closer at the green and the blue term. So the green term here describes fluid-fluid interactions. We here use a model based on PCSAFT. This is just one example for a molecular model that is commonly used in our field, but there are many other models that you could use. And basically, this is the most important part, I would say, in our work to find good molecular models that describe what's actually going on in the systems. Okay, how does this work? For getting the whole energy, we just sum up different contributions from our molecular interactions. We start off by having an ideal gas, but there are no direct attractive interactions here. Then we go on and have a hard sphere system. Hard spheres are like bowling balls that can bump into each other, but they don't attract in between them. Then we can form hard chains. Why is that? Because real molecules are typically not spheres. They are more like elongated. Think of alkanes, something like propane, butane. They're chains of individual atoms, basically. And then we have different kinds of attractive interactions. We could have dispersive interactions, something like van der Waals forces, associative interactions like hydrogen bonds, or polar interactions if the molecules in the system are polar. Okay, Then the blue term describes how the solid affects the fluid in our system. And this is also quite important. We can describe these solid-fluid interactions with several different equations. This is just one approach that is commonly used. And how we do it, we have our system that is then divided into grid cells. Like you may know from any simulation, you need to define certain grid. Then we put fluid molecules here in green in this grid cell. And then we evaluate all the interactions between this green molecule with all the solid atoms. See, these red points are supposed to be solid atoms. And we do that in every grid cell. And by this, we can determine this external potential that then enters the equation at the top. Okay. I want to show you today two applications of this DFT approach. One is to contact angles, and we did there, of course, the theoretical calculations, but we also did experiments to compare our results to. For those of you who don't know what a contact angle is, we're talking about droplets who are sitting on a solid surface, and we're basically interested in this angle theta here. This is relevant in many, many fields. So for example, in material science, if you have, I don't know, guys, if you have a rain jacket, but if you have a raindrop on your rain jacket, then the droplet will immediately roll away. But on the other hand, if you have a t-shirt and your water drop falls down, then the water will immediately go into your t-shirt. Why is that? That's because the contact angle of these materials with water is different. So this is an important quantity to know, but not only for material science, also it's important in many areas of the industry. If you have, I don't know, there are some, how do you say it, heat exchangers where you can improve the efficiency by having a large contact angle with water. So for example, the water doesn't stick to the walls of the heat exchanger, but just flows away. There are many examples where this is relevant. Okay, how do we use DFT to determine the contact angle? We employ Young's equation that relates the contact angle to the interfacial tensions, and the interfacial tensions we can then determine from the DFT approach. For that, we again need an external potential. Since we don't really know in our experiment, we're using some PTFE, some Teflon, how exactly this is built up molecularly. We're just using one measurement of the contact angle of octane to characterize basically the solid to fluid energy interactions. And then we can predict the contact angle of all other substances that we looked at. And we did that for a huge variety of substances. Here I show you the contact angle from theory, from the DFT on the y-axis, and on the x-axis there's experimental values. So the perfect results would be on the diagonal in this plot. And as you can see, quite some points in blue are close to the diagonal here, which means that the theory agrees quite nicely with the experiments. There's some results that are a bit off of the diagonal. This is these monohydric alcohols. We tried a different approach here. I don't want to talk too much about this, which makes the results a bit better, but still for this kind of substances, there's a bit of a deviation that we found. But nevertheless, for all the other substances, we get an average deviation of 5.1 degrees, which is really good because even if you're doing the same experiments on 2 different days, you could easily have a deviation in the experiments in this order of magnitude. And then we extended this approach to mixtures as well. So we looked at mixtures with octane, with toluene, with water. You might think, oh, water is an easy substance because in the lab it's quite easy to handle water. But as soon as you go to molecular theories, this is like the final opponent. It's very difficult because of all these hydrogen bonds that appear in water to model. And basically our finding was that once you have a good description or good results for the pure component, you also get a good description for the mixtures using our model. A second application that I want to talk about is solvation-free energies. I don't know if you heard of that. It's defined. It's defined from this equation up here. So basically, we can use this grand canonical functional that we use in DFT anyway to determine the solvation-free energy. But why is it relevant? That's because it basically describes the energy that is released or that is needed to dissolve a molecule in a liquid. And this is especially important in the medical industry. Think of painkillers. If you take painkillers, then the molecules, they have to somehow go into your blood to actually do something to your body, right? So for the medical industry, it's really important to know beforehand when they develop a new drug candidate, does this dissolve in the human body or not? This depends a lot or decides a lot about if the drug will be successful in the end. So methods to determine the salvation-free energy are always very helpful in this context. And what we did is we used our DFT approach to calculate salvation-free energies and compared that to experiments. This time we didn't do them ourselves, we used a database for this, and we found that we can get quite a good agreement, much better agreement than the usual simple approaches that are used, and only models that use practically this kind of experimental data already as an input in the model had more accuracy than our models. And for us, we didn't use any information about salvation-free energies. We just took our molecular model and came up practically with these results. Okay. Yes, this was my research on DFT. I'm now jumping forward to the next topic. This is the hydrodynamic DFT. So we're now going from equilibrium systems, where nothing is moving basically, to non-equilibrium systems. And the basic idea here is to use balance equations. I guess you guys have heard of balance equations before. So we're using a mass balance. We might as well for mixtures use a component balance, but here for simplicity, I just show the mass balance. And a momentum balance. And this momentum balance, we have a term from DFT. This is the same term that appears in the DFT equations. And this practically takes into account how fluid-fluid and solid-fluid interactions change the behavior of the system. So how an interface acts on the overall system behavior. Interesting about this model is that if we don't look at an interface, so if we go far away from an interface, the model becomes the Navier-Stokes equations or the isothermal version of that you might know from your fluid dynamics classes. And the stress tensor that appears here, we model by assuming a Newtonian fluid, and for that we need a viscosity in the system. And because in an interface, the viscosity can change, right? If you just look at a fluid, the viscosity is almost the same everywhere. In a gas, the same. But in between, we don't really know what the viscosity is. So we need a model for that. And this I also worked on in my PhD, but today I didn't have the time to go into detail about that. So let's go to one application. Remember, now we're looking at a really small scale, again, a molecular scale. And what we see here are density profiles from droplets. On the left side from DFT, on the right side from molecular dynamic simulations. Again, molecular dynamic simulations are the reference for us. We try to find results in agreement with MD. And what we can see here is the density profile of the droplet. We can see already they look quite similar. And up here, I put the contact angle, again, of these droplets. And we can again see they are also quite similar. There are two interesting things that you might find surprising or interesting. I don't know how good you can see it, but there's some kind of layering. There's more yellow, then more dark, then more yellow, then more dark, when you go practically away from the solid. So down here is the solid, this is the liquid, and here around this vapor. You see this kind of layering is the same that I mentioned in the beginning. When you have a solid and you have this adsorption to the solid, you get a molecular layering at the solid. And this can be seen in our theory as well. And then you might wonder what this wavy structure is. So again, we're looking at a really small scale, and the solid consists of individual atoms. So you can actually see the effect of the atoms on this density profile by this wavy structure. Okay, we have this agreement here between the two methods, so we can use them as the starting profile or initial profiles for the dynamic simulations that I actually want to look at. But before I do that, I want to show you how the viscosity in our system is modeled. Because before I said we need the viscosity at every point in the system, right? And in my PhD, I also developed a model that's called, well, I generalized or used a model and further developed it that can be used to determine the viscosity in a system. And this leads to a quite complicated behavior of the viscosity in a droplet, right? There's this crazy thing going on at this interface. To actually see or to quantify if this is needed, we also used a simplified model we called bulk model, because we just use one value in the droplet and one value for the viscosity outside of the droplet. And I will show you how this affects the results in a minute. Okay, I hope today the video is working. We're looking now at the dynamic simulations. On the left side, there is results from hydrodynamic DFT with this complicated viscosity model. On the right side with this easy or simplified viscosity model, and in the center there's the molecular dynamic simulations, NE is non-equilibrium, that we take as a reference. So we hope that our approach agrees with this molecular dynamic simulations approach. Okay, if I start the simulation, then you can see the droplet is moving to the right. Why? Because we apply a force. We just add a force, something like gravity. But on a small scale, this is a much, much larger force. We can see the droplet deforms a little bit and moves throughout the system. We use here periodic boundary conditions. So once the droplet leaves on one side, it enters from the other side. After some time, there is a steady state. So the droplet moves with a constant velocity, and we can average the density profiles during time. So we get a nice and sharp density profile, and we can determine the contact angles again. Now, since the droplet is deformed, we have different contact angles in the advancing and in the receding region. So advancing region is this one, receding region is this one, and we get different contact angles here. We can then see that the contact angles between the different approaches are quite similar, especially between the left one and the center one. Okay, now I want to check what happens if I use only half the force that I used before. We can then see that the droplet deforms much less. If I use twice the force that I used before, we can see that the droplets deform much more than before. For all these cases, we see that the left column and the center column, they look quite similar. So we can say there's quite good agreement. With the simplified viscosity model on the right, for the low forces, it's kind of okay, the agreement here. For the large forces, you can see the shape of the droplet looks quite different from the reference simulation. Okay, now I showed you something about the density profiles and the contact angles. But how does the velocity profile in the system looks like? Because the droplet is moving. There's actually a lot of stuff to discuss about this density profile, but about this velocity profile. But I want to talk about one thing in particular. That is here in the contact regions, in the front and in the back, the velocity is not zero. So there's a lot of discussion about this specific effect in literature. Like, I mean, a really, really big amount of papers on this. And it's really interesting that we can reproduce this effect by using a continuum approach, basically, a continuous balance equation approach. Okay, moving on, there is one more thing that's interesting. You can kind of see that the velocity vectors point to the top here and down here. So how is this droplet actually moving over the surface? For that, I will show you the video again that I showed you before. But this time, I marked one point in red, and this point will now follow the streamline starting from the current position. Oh, and I play the video a bit faster. So you see this red point just moves along the solid, the vapor-liquid interface until it reaches the solid about now. And there it more or less waits until the back end of the droplet comes, and then you can see that this moves along the vapor-liquid interface again. So what you can see here is that the droplet is not just sliding over the interface, but it's actually more or less kind of rolling over the interface. And this was quite interesting for us to see. We can see that even better if we look at the velocity relative to the center of mass velocity. So we take the average velocity of the droplet and we subtract that from every velocity at each point. And we can see that there is some kind of rotation that is overlaying just the translational motion. If we compare that to molecular dynamics simulations, we get quite similar results, and this is quite nice for us. There's one important point I want to say. In our method, we get the velocity profile, because we're solving balance equations, at every time step with perfect accuracy. So that means there's no statistical uncertainty. But in the molecular dynamics simulations, since we are averaging over many, many time steps, there's a lot of statistical uncertainty, right? The molecules, they just have a random movement that they always do on top of the movement that is basically on average done. So we need to do a long simulation to get this kind of result. And from our new approach, this can be determined quite easily for every time step. Okay, for completeness, here's the result from hydrodynamic DFT with the simplified viscosity model. Again, we see that the results are in much better agreement with this more complicated model for the viscosity. With this, I come to the end of my scientific talk about my work in Germany. I basically looked at density functional theory for equilibrium systems, contact angles, salvation-free energies. Then I looked at transport coefficients. I didn't talk about that so much today, but we saw in the results from the final part, from the hydrodynamic TFT, that we actually need this viscosity model to get really good results. And then finally, I looked at these tiny droplets on a small scale and basically found that the agreement with molecular simulations is quite good. What next? The past few months before I came here, we worked on improving the reducing the computational time of our model, because it is quite slow, and we now try to use GPU parallelization approaches that are typically used for artificial intelligence. So we kind of use these computational tools to speed up our simulations. And with this, now we can look at a variety of cases, like the coalescence of droplets, the filling of a pore. Yeah, this is a solid material with a pore, and the liquid just fills up this pore. Or similarly here, you have a pore and the liquid is flowing. Here's a gas stream that kind of pushes the droplet to the side. There's a huge variety of applications that can be studied with this. And of course, we need to figure out a way how to compare this or how to translate this to the large scale in the end. Okay, here's some references. I don't know if this is interesting for you. I can show it again later. And I will now go to the third part of my talk today. Perfect. Yes, so in this third part, I will talk about my work here with Professor Luis about one application of molecular theories to an actual industrial process. Before, I showed you some applications of DFT to some phenomena, but this here was now an approach, or is an approach to actually use that in a real process from industry. So we looked at temperature swing adsorption. What is that? Basically, the idea is to separate a mixture of gases. Think of a power plant where you have nitrogen and CO2 as a product. Of course, we don't want CO2 to go into the atmosphere because of climate change, right? We want to separate that from nitrogen and store it in the ground or somewhere else. And we're here making use of the different tendency of different molecules to adsorb to a solid. If you choose the correct solid, then we can make use of this. So here, for example, I will show you the loading. So this is basically how much of one substance can adsorb to a solid for CO2 and nitrogen. For CO2, it's quite large. For nitrogen, it's quite low. And we can use this to separate these two substances. There's one more interesting thing. So for the loading of CO2 that I want to talk about. So if you increase the pressure, you get a higher loading. If you increase the temperature, you get a lower loading. This can be also employed in this process that I will show you now. The process works like this. So we have an adsorption step. We have the feed of CO2 and nitrogen going into the column. The column is filled with particles of the solid material that is porous, like a porous medium. And because of the CO2 has a much higher loading, it will fill up all this solid in here, while the nitrogen just more or less goes through this reactor, or through this column. So we get as a product almost pure nitrogen at the beginning. Then at some point, when this solid is filled up with CO2, also CO2 would come out here, so we stop the process, and then we increase the temperature. Remember what happens when we increase the temperature? Then the loading drops. This means that the CO2 goes from the solid phase to the gas phase again. And we can then withdraw or take out CO2 from our column. And then at the end, we want to get back to the initial stage here, so we need to cool down our system again so that we can start from the beginning. In reality, we actually use more than one column. We use several columns to have a continuous cycle because we don't want to, we cannot tell the power plant to stop its process because we need to change something here. So we use multiple columns for doing that. As engineers, what is our job? We want to model the system, of course. In the end, we want to be able to optimize it to try to find the perfect operating conditions. So we need a model for that. We here use, of course, balance equations. We start off with a component or a mass balance. We have terms like storage, advection, or convection, diffusion. And in the end, the most important part for this application is this adsorption term. This partial n over partial t is basically the adsorption rate. That means if a molecule adsorbs, if a certain amount of this molecule absorbs over time, then this reduces the concentration of this gas in the gas phase. Makes sense, right? However, this adsorption is not instantaneous. It takes some time to adsorb. And this time dependence is basically also written again in another differential equation. So we here have the equilibrium loading with this EQ, and this is the current loading. So the equilibrium loading is the loading that we would have if we would wait forever. So we have practically the rate of this adsorption determined by the difference between the equilibrium and the actual current loading. Then we need to look at energy balances because we want to be able to heat up our system, right? So we have this energy balance. The temperature change is related to several terms. So we have here some heat contribution through adsorption. If you have a lot of adsorption, this releases heat or releases energy and can heat up the system. Then we have convective transport or advective transport. We have thermal conduction. And then we have here a term that transports energy from the bed to the wall of the column, because the column has, of course, the wall around, like something like steel. For this wall, we again have a energy balance. Here we have conduction. We have this same term that we had before, right? So the heat transfer from the column bed to the column wall, and then from the column wall to the ambient conditions, to the air or something that is surrounding our column. Okay. Yes. So why am I showing you all these equations and these models? The point I want to make is there are a lot of parameters that we don't know. This dispersion coefficient, this mass transfer coefficient, this equilibrium loading, the heat of adsorption or enthalpy of adsorption, thermal conductivity, heat transfer coefficients. All of these need to be determined somehow. We could use engineering like correlations, which is, I guess, most typically done in industry. We could do experiments to fit them to. But in our case, what we try to do and what we would like to do is use molecular models for the prediction of these values, with as little experimental information as possible to determine these quantities. So here we start off by focusing on this equilibrium loading and using an approach for that. Here I show you some results for breakthrough curves. What is a breakthrough curve? This basically is the composition, mole fraction of a gas at the outlet of the column. So we put in a feed in the column and we look what comes out at the top. Here are three types of results. So first, experiments from literature with these crosses. Then the red dashed line is a model from literature where they use a Langmuir isotherm model. So really a simple model which needs to be parameterized by a lot of experimental data. You need quite a substantial amount of experiments to get a good description for this. And then finally, there's our own model in green, where we basically used a confined equation of state, something that is it's not similar, but has the same idea as density functional theory that I introduced above. It's basically a molecular approach to determine this adsorption loading that I was talking about before, or the adsorption isotherms if there's the whole curve. Okay, what happens here? We have almost immediately a breakthrough of nitrogen, right? It doesn't adsorb, as I said before, so the nitrogen comes out at the top almost right away. And then we have pure nitrogen at the top, a mole fraction of 1. The CO2 does not break through at the beginning because it adsorbs in the column. And after some time, the CO2 breaks through and it reaches the feed condition or field mode fraction of 0.3. And of course, the nitrogen has to drop to the feed mole fraction as well, which is 0.7. Okay, this was done with, for us, as you see, this is the same, more or less the same result between our model and the model from literature, which is a good result actually, because we want to use our molecular model to get the same result that we would use if we use a lot of experimental data. Because in the future, if we, for example, develop a new system, if we look at something where we don't have experimental data, we want to get the same result without having to do many, many experiments. Okay, there are of course many next steps to do. This was just the start of this project. We could use DFT that I showed you before, which is a bit more predictive than the confined equation of state. Or we could use, or look at other parameters from molecular models, for example, this enthalpy of adsorption or thermal conductivity in our system. Let me check the time. Okay, yes, I still have a bit of time left to talk about, in the fourth part of the presentation, about something non-scientific at all, about the life and the PhD in Germany. I hope this is of interest for you guys. So first of all, Stuttgart in Germany, where is it? Here you can see if you take a plane from Garullos to Stuttgart, this is quite a long distance, and you would be in the center of Europe here. Then zooming in, you here have Germany. Stuttgart is in the southwest. It's a southwestern state called Baden-Württemberg, quite complicated. Our neighbor is Bavaria. Munich is in Bavaria. You might have heard of that, where Oktoberfest is going on. So I will talk a bit about the south of Germany later. I have one question for you guys. What do you think? How many times does the state of Minas Gerais fit into Germany in terms of the area? Somebody? Twice. Good guess, but it's actually the opposite way around. Minas Gerais is like, you can see here, not almost twice, but 1.5 times as large as Germany. One more question. Distance between Sao Paulo and Belo Horizonte compared to the distance between Stuttgart and Paris. Now you might know what I'm talking about. It's almost the same. So something that is for you kind of close is for us already quite far. Europe is much closer. Everything is much closer together compared to Brazil. This is one of the first learnings I had when I came here, how far apart everything is. Okay. Why would it be interesting for you as engineers to go to the south of Germany? We have a lot of industry. You might know a few of these brands: cars, Mercedes-Benz or Porsche, BMW and Audi, international brands that are all in the south of Germany. The first two in Stuttgart, the other two more in the direction of Munich. We have a lot of chemical industry. The BASF is one of the biggest chemical companies in the world. Linde produces gases. I don't know if you heard of that. Bosch and Mahle are mechanical engineering companies who produce parts for cars, but also tools, or Bosch produces fridges and washing machines and all crazy kinds of things. So huge international companies. We also have, well, these are not technically engineering companies, but also big companies you might know. SAP for accounting and industry. Allianz is one of the biggest insurances in the world. And then we have Zeiss, even though it's not so popular internationally, it's quite important in the manufacturing process of microchips, because they produce optical components, which as far as I know, are used in a huge amount, or a huge percentage of the production of microchips worldwide. Okay, this is actually one thing about the south of Germany. We have a lot of medium-sized companies who are really good in what they're doing, but they're just doing a specific thing and they're doing it very good, on a side note. Okay, but it's not only work that is interesting, or that could be interesting for you guys in Germany. It's also what you can do in your free time. We have a lot of culture, a lot of nice buildings, castles like that. We have culture in terms of operas. The Stuttgart Ballet is quite famous, even though I'm not so much into that, but it's apparently really good. We also have a lot of museums. Here, this is the Mercedes-Benz Museum in Stuttgart, really nice. If you're more into football, there's also enough for you to see there. The Bundesliga with my home team, VfB Stuttgart, it's really good. Really nice atmosphere to go there. Or if you're more into partying, then you could try the Oktoberfest. But we actually have in our city, in Stuttgart, something almost as big and almost as nice, I would say, as the Oktoberfest. So there's in many cities actually something similar. And then, of course, there's beautiful nature in terms of the mountains, the Black Forest, where you can go hiking, mountain biking, all that kind of things. Okay, of course, I also want to do have some time left, talk a bit about the University of Stuttgart, where I did basically all my academic career so far, or most of it. We are a medium-sized university, I would say, 21,000 students, 270 professors, a budget of 3.6 billion reais, I think, 625 million euros. We have a lot of international students, actually. I wasn't fully aware of that. I knew there were many, but when I looked the numbers up, it was quite surprising to me. It's quite a large number, I think. And the engineering campus is a bit outside of the city. It's more close to nature. It's quite nice. It's not so crowded and loud, as compared to the downtown campus for social sciences. This is quite noisy. Because for me, that was something new. I didn't know that. The way of studying, so the division, or like the combination of bachelor and master is a bit different in Germany. So I just want to briefly mention that because our bachelor is only 3 years. I think here it's much more, 5 years or something like that. And we do only fundamental courses in a short thesis there. Then you would do the master's, and almost everybody who does the bachelor does the master, because the bachelor in Germany is, because it's only 3 years, not so renowned in industry. So we mostly do the master's as well. And there we again have 3 semesters of courses. And then we do 1 thesis that would be 6 months. And you could do internships sometimes, depending on the course, you have to do internships. If you like research, then you would stay and do a PhD. In Germany, we call that something else. If you ever look on a website, don't be confused. That typically takes 4 to 6 years. You do research, you do, depending on the institute, teaching or acquisition of funding, something like that, and courses, but they are voluntarily. You don't have to do courses, they're just there to help you, and to do also soft skill courses, writing courses, something like that. A lot of funding in the university comes from industry, but a lot of funding also comes from the state. And what's specifically interesting is there that we have something like clusters or big research centers where huge, like say 10, 15 professors from different institutes are funded all together. And the idea is that they can work together quite nicely. So I'm funded in this CRC 1313 for Porous Media, and it's quite good if you have the chance to work in one of these clusters or research centers, I would say. My team in Stuttgart is called ITT. We have 2 professors, my supervisor, Joachim Groß. We have 3 postdocs. Maybe interesting for you is that we have 1 woman from Brazil, Marceli. She did her PhD here with Professor Luis. Then she went abroad to Germany, actually, for like a research stay. Then she went to, as a postdoc, to Qatar and other places. And then she came back to Germany as a postdoc. So maybe for you guys, it's a hint that it's not so bad to live and work in Germany. We have 10 PhD students. I would say really, really nice people there. So if you ever plan to come, I'm sure you will have a good time as well. In terms of research, we more or less do all the things that I talked about in my scientific part of the talk. So basically we use very fundamental methods in terms of physics, chemistry, but always with the engineering application in mind. It's not just about knowing stuff or understanding stuff, but also about the application of that. We also teach a lot of bachelor and master courses. If you're interested, you can ask me later about that. Final slide. A PhD at my group in Germany and in general in Germany. As a disclaimer, I have to say not all the information I give here apply to all the institutes in Germany. It always depends a bit on the professor and on the institute. But in general, you do scientific research, of course. You have to do some kind of teaching. So you help the professor, you create sometimes exams, stuff like that. You give not lectures, but like trainings with the students and stuff like that. You do courses for yourself if you want, and you have student supervision. So if you have a master's student who wants to do a thesis, you supervise them. Of course, in the end, the professor gives the grade, but you interact a lot with the student, and this also helps quite a bit in your personal development, I would say. Then, of course, you have a quite large freedom in terms of your research topic. You can decide a lot by yourself, and there's little external pressure. So the professors not often come to you and tell you, oh, you need this and this and this by that date. It's more your own thing. And in the end, you just need to have something like 3 journal publications for a successful PhD. Could be less, could be more, depending on the extent of this publication. But if you're not motivated enough yourself, you don't do research, then you might not have a PhD at the end, but you still have an experience. Okay, everybody has to decide how he wants to do it. Most PhD students go to industry afterwards in Germany, because in Germany, especially in the south, where I told you before, all the companies that we have, there's also quite a bit of research positions in industry. So even if you want to do research after your PhD, you can do that in industry. This is what many people do. Some also stay at the universities or go to other universities in Europe. As I said before, distances are not always huge. You could go to even another country, Switzerland, for example, in 2 hours or something like that, driving. So some people also stay at the university, do a postdoc, and then try to get a professor. But this is always, in every country, quite difficult to do, to accomplish that. Okay, the funding in my institute, we get a full position for 4 years, and then if there's some reason for extending, it could be extended to up to 6 years, I would say. Yeah, so how would you be able to do a PhD in Germany? The easiest way probably is to do a PhD here and then to make a research stay like I'm doing here, just the opposite way in Germany. Something like 3 to 12 months. This is relatively easy. You just ask your professor here, or you directly ask your professor in Germany to make some contact, to ask them about it, and then you can try to do this research stay. Something that some people I know here are also doing is a double degree, where you spend like half the time in another country, half the time here in Brazil, and then you have two supervisors or more than two supervisors, who help you with your PhD or supervise your PhD. If you really want your full PhD in Germany, this is a bit more complicated because the German system can be quite complex, not only for foreigners, but also for Germans. But you would have basically to directly contact the professor about open positions, and then you would have to do all the bureaucratic stuff, but you can do that. And sometimes it's helpful to have or find a scholarship as well. So here, I'm not an expert, I'm sorry, I don't really know a lot about this. I just know that this website is from the government in Germany. This gives a good, nice overview of all the basically different ways to do a PhD in Germany. And then we have 3 institutions that fund such projects. So, for example, the DAAD, it's a German academic exchange service that also funded my stay in the United States during the bachelor's. We have the DFG, German, I don't know how it's translated, sorry. The DFG that funds a lot of research projects, as well as doctoral stays and postdocs and professors. And then we, of course, have the European Union that also has grants. So if you're interested in that, you can ask me later, but I'm, as I said, not an expert, or try to ask your professor here or try to find something in the internet about that. But it's possible, I know that. Okay, with this, I end my talk for today. I would like to thank again my supervisor in Germany, Joachim Groß, and my supervisor here, Professor Luis. And thanks for the organization and you guys for listening in, and feel free to ask questions.
Okay. Thank you very much, Benjamin. That was a very nice talk. I would like to open the room for questions.
Thank you for your presentation. Very nice things that you work. I'm of the field of fuel cells. I research fuel cells here at Unicamp, and you talked about it briefly in the beginning. I'm kind of curious about the implications and applications of what your simulations. What I heard about density functional theory, it's very used in catalysis for interactions between the specific catalyst and the fluids that you react with to predict reaction steps and all that. Do you think that's feasible? Like that's the way that you could work with in fuel cells?
Yeah, very good question. I think that's something I didn't mention. So there's actually 2 kinds of density functional theory. There's the one I had it on the slides. I didn't go into that. It's what I'm using is classical density functional theory. So we basically look at fluids in contact with a solid. And I guess, I'm not entirely sure, but I guess what you're talking about is the quantum or electronic DFT. So that's a method that uses the same mathematical framework. That's why they have the same name. So basically you have a functional for an energy and that is minimized, and then you get a density out of it. But in your case, it would be the electron density around the solid. So you can determine the solid structure of a material, for example, to determine the catalyst sites or where the reaction is taking place, something like that. So if you would like to apply classical DFT to fuel cells, I mean, for sure, something like the diffusion through this porous medium. As I said, there's this porous, I'm not an expert in fuel cell, but there's this porous layer where gas diffuses through. Then if you look at this gas diffusion, for sure, you could use classical DFT to get an idea how the density profile looks. You could use even the dynamic method to understand a bit better how the flow through this solid material is affected by, let's say, geometry, the material itself. But if you look at catalysis, then you would need to have the electronic DFT. Yeah.
Okay, more questions? I have a question. In your simulation of the adsorption process, did you can you add contaminants to the stream? Not only CO2 and nitrogen, but also other contaminants, and contaminants that might make stronger bonds to the solid, like irreversible interaction.
Yeah, so thank you for the question. That's actually, I didn't mention that, but that's the ultimate goal of the process, because we're looking at adsorption in CAF20, a solid that is pretty good for CO2 and N2 separation. But most of the solids or most of the solid materials have the problem that as soon as there's water in the gas, then the water adsorbs much, much stronger than the CO2, right? And especially there can be something like at the beginning, if you have like a low concentration of water, relative humidity, you get a lot of CO2 adsorption, and then as soon as the water comes in, the CO2 adsorption almost drops to zero, something like, it's called competitive adsorption. And this is actually the ultimate goal, to look at a situation where you have water in the system, because in such a case where the adsorption isotherm is not this typical Langmuir type, but more complex behaviors, then a molecular model is, at least we expect it to be more accurate than this Langmuir behavior. Because in most publications that exist so far, it's always assumed that you have a drying unit before you look at the process model. But in reality, that might not always be the case.
Okay, so the experimental stuff that you showed over there, the reference was from 2020, I think. It was like a synthetic mixture of gases, a synthetic mixture of N2 and CO2.
Yes, yes, yeah, from a
Yeah.
research paper. Yeah.
Okay, so more questions? Luis, do you want to say something? Okay.
So, Benny, what are your plans for later, postdoc or industry?
Oh, good question. So I'm not fully done with my 4 years yet. So when I come back home, I still have some time left to think about that. I really enjoy doing research. I really enjoyed all the time in my PhD in Germany here a lot. So I don't actually know. It's quite difficult to decide, because both are good options, to be honest. Yeah. But thanks for the question.
More questions? I noticed that you bring Minas Gerais to your presentation. Have you been there?
No, unfortunately not. But I know some of my colleagues from there. They
All right. I used to say that Minas Gerais is like the Tuscany. Have you been to Tuscany, Italy?
Yes.
It's like the Tuscany of Brazil.
Oh, nice.
Because of the food. Yes. I think it's a good comparison. Very good comparison.
Nice.
Well,
Yes.
guys, Benny, I have a little souvenir from the School of Chemical Engineering for you.
Oh, thank you very much.
And I would like to thank you again for your presentation.
Yes, thanks for having me.
Everyone, we have a coffee break on the hall. Please feel free to ask questions to Benny, talk a bit more to him, ask questions about Germany, how is life there. You don't need to speak German to go to Germany, okay? Remember that. And also talk to Flavia, ask questions about the student representative role and the importance of this for our graduate program, okay? Thank you very much, and bye-bye.
Bye-bye.